Okay, so today our speaker is Polina Baron, and she will tell us about Schrödinger operators and their spectral theory. Please.
Thank you. Let me check if everyone sees the file. Yeah, I think the demonstration.
Yes, we can see.
Great. Today I'm going to give a very expository talk. The aim of which is to introduce the audience to a new topic, a new area of research, which is actually very prolific and has been for quite a while, and had at least one Fields Medal awarded for progress in this area. So I'm expecting that a lot of people might find it very interesting to study. And to boot, it has a lot of Russian researchers who contributed to it significantly. So everybody probably encountered in their life at some point a so-called Schrödinger equation, which was introduced in 1925 and which is of the following form. Or if we rewrite it in a more math-friendly way, just like that, where psi is just a function from L2. And this, one might note, looks like a Hamiltonian of a system, and that's why it's denoted by H. And this operator is a Schrödinger operator. It acts on L2, and we can usually write it in the following form. H equals minus Laplacian plus some function V, which is just the potential function, and which we are interested in, changing. So if we change the function V, we actually receive very different results on how the operator acts on the space of functions. And that's one of the main topics we're going to discuss today. And people like to define a discrete analog of the Hamiltonian, of this Schrödinger operator, because it appears as a Hamiltonian in many discrete cases. For example, if we study some problems on lattices, or in topology when we study simplices. So we just rewrite it in a discrete form, and we get function psi from x plus some period, function psi plus x minus some period, plus the function psi multiplied by our function v, which is dependent on x and period. And the period might be different, it might be the same, it might not matter at all. And the way there are a plethora of ways of choosing this function, and they're all interesting to different kinds of people. So this form is actually somewhat canonical, and it's can be written in the following way, where U and big U and big B are defined in the following manner, and they are called Weyl operators, and they are related to the so-called Weyl equation, as in if we write them in the following manner, we'll receive this equation on them, and we will see that the Schrödinger operator is a trace of the so-called L operator corresponding to the Weyl equation. I decided not to include it here because I confess the literature is very misleading, with a lot of links to very old articles that were published in like processings of some Chelyabinsk 7th conference on something, and they're incredibly hard to find. So tracing the definitions and their correctness back to the source appeared to be a real problem. But it sort of makes sense that the Schrödinger operators arise a lot of different areas of mathematics because we can perceive them, as I said, as a Hamiltonian of a system. And we are going to discuss their properties, and we're going to do it in the following setting, with a discrete setting, because it's still interesting, much simpler, and gives us a lot of information on the spectrum, which we can try to generalize to.
Sorry to understand, what is Q on the previous slide? Q.
Come again?
Q. How Q is defined here?
That's just a number. It's a number like a number from the real number line, and it can be 0, it can be 1, and I think that otherwise it's free to go.
It's not between 0 and 1, it's any number, or between 0 and 1.
It can be any number except 0 because it doesn't make any sense. And I think that people generally don't like the case of 1 because it's so this is one of the equations defining a so-called quantum group. And as far as I'm aware, people sort of escape having Q equal to 1 because in this case, the group ceases to be quantum. But I'm not an expert, and that might not be true.
Thanks.
The U and V are just some unitary operators.
Sorry, come again?
U and V unitary operators, and we have such non-commutative relation between them.
Yeah. Right. So what we're going to do today is we're going to study the properties of the operator, the Schrödinger operator, and we're going to do it in several settings where we define the function v, the potential function, in different manner. And we're going to mostly study the spectrum theory for reasons I will come to a little bit later. And first, let's just discuss the setting, like where we're at and what space we're at. So for the rest of the talk, we will assume that we are working, we're working in L to Z space, which is just the space of all functions, which have bounded sums of norms of those functions at the points of Z. And the product is defined in the usual manner, and we can define everything we need. We can define the norm, we can define the metric in just the usual manner. And the only, so basically the only really important conditions that we are to set are that that our operator H is bounded and that is self-adjoint. And now we're going to discuss the spectrum. And the classical way of studying the classical way of studying the Schrödinger operators, I should probably say that, is through separation of variables, because we have time-dependent variables on one side of the equation and space-dependent variables on another side of the equation. And this idea prompts one to think of the Birkhoff theorem from ergodic theory, which states some results on how time evolution and space evolution can be connected to each other. And that will be the reason why we will at some point study dynamical potentials. But also I have to note that there is a very nice connection between the solutions of the equation and the spectral properties of the associated operator. And informally speaking, just to prepare you for what's going to follow, the slower the solutions of this equation decay or grow, it doesn't matter. The more continuous the spectral measures are going to be. Spectral measures I will probably have to define because I don't think everyone knows that. And sorry? Sorry? Was that a question?
No.
May I ask a very naive question? H includes Laplace operator. How it could be bounded? You know, Laplace operator is not bounded. V may be bounded. That's fine. If the potential is bounded, but Laplace operator is not bounded.
Well, I have to refer you to here and remind you that we'll.
Oh, it's a discrete case.
Say an analog. Yeah, of course, that will be a problem if we had. Yeah, if it was a continuous analog, it would be a major problem, and actually is a major problem, and that's why some of the techniques we're going to discuss are not very well. But we will not be capable of adapting them for the continuous case, and the continuous case forms people to study
specifically
different,
okay, fine.
Yeah, different things. So the spectrum is just our usual definition of the spectrum. We are studying, we're searching for the numbers E such that H minus E has no inverse. I note that this is a standard notation, but by no means should we assume that this is the identity matrix or operator or anything. It can be a number. It's a constant operator, strictly speaking. But we are working with, and also it might be important to note that the reason why we are in the real numbers, not the complex ones, is the self-adjointness, because otherwise we will have been dealing with complex numbers. So there is a quite, normal, quite common way of defining the so-called spectral measures for every function from L to Z. And the spectral measures are such, they're defined just like that, very boring. And for them, a very nice property holds if we apply a function to, if we apply a function, I'm sorry, this is a mistake. It should be a function from R to the complex numbers. But if we apply a function from R to the complex numbers to our operator, and we consider the following product, then we will receive just an integral of a function over the measure. And we can always consider the decomposition of measures into an absolutely continuous piece, a singular continuous piece, and a pure point piece. AC, SC, PP for shortness. And nothing stops us from defining a measure decomposition of the L2Z into subsets L2Z AC, L2Z SC, and L2Z pure point. And we just say that a function is in L2Z AC space if its measure, its spectral measure is absolutely continuous. And we do an analogous thing for L2Z, C, and pure points. Now, we want to study the spectrum. We say that the spectrum is absolutely continuous. We say that we say, and that's a little bit confusing, that the part of the spectrum that corresponds to this subset is the absolutely continuous spectrum, but we say that the operator has purely absolutely continuous spectrum if in this decomposition, those two cases vanish. Those are not equal. Those are not identical. But unfortunately, we sort of have to use this notation because it's very old. Now, there is a famous range theorem after real and range of just coordinates that allows us to say some things about the behavior of the solutions of the time-dependent Schrödinger equation in case the initial state, we'll call it psi 0, belongs to one of the subspaces above. So if it's just pure point spectrum, then it's quite boring. We just have this sum. It's summable. It's less than epsilon for any epsilon. At least we can find them such that it's less than epsilon. And if psi 0 is inside absolutely continuous or singularly continuous piece, then we can consider the limit, which will go to 0. And if it's in the absolutely continuous case, but not in the singularly continuous case, then this limit will also tend to 0. So in other words, if the spectral measure is pure point, then the evolution can be confined to some finite set, or at least an arbitrary small portion or portion of the total weight. And if the spectral measure of the initial state is continuous, then the evolution after its time averaged will leave any set, any finite set, which is completely different. And if it's absolutely continuous, then it leaves any set without time averaging. So the more continuous the spectral measure, the more the evolution spreads out in space with time. And we will devote to about, well, some time to making this statement I just said more quantitative.
In condition C, you mean for any n capital, not n small, yes? Do I understand right?
Right, for any n capital, I'm sorry. Yeah. You're quite right. So we consider our equation, which we have already seen, but just for the sake of remembering it, because we will use it quite a lot. And we want to study the behavior of the spectrum. And we can define as some sort of a universal measure, which is very nice because every spectral measure will be continuous with respect to this universal measure.
Sorry, we put measure on the space of states, or on which space we?
No, it's a measure on the space. It's a measure on the space of the space of sets. It's not a measure on the space of functions. It's a measure on the space of states.
Thanks.
Measure such that every spectral measure will be absolutely continuous with respect to this measure. Because in this case, we will be able to discuss the spectrum without depending on a specific function on L2Z. Because we've received a nice result, but it depends on a function from the L2Z space, which is not very nice. And we want to get rid of this dependence. So we redefine the spectral decomposition, and we just say that absolutely continuous spectrum is the one that supports the absolutely continuous part of the new universal measure, and so on. Basically, a result that we get for free is the following, is that we can define the viewpoint spectrum plot as a closure of eigenvalues. There's a minimal support of the measure of the viewpoint part of the universal measure will be given by the set of the eigenvalues, because the complement of this set will have zero weight with regard to this measure. And so we do have an incentive to consider the following equation, which is called time-independent Schrödinger equation. And we want to define, we want to note that this equation is actually defined by U0 and U1 and Bn. That's enough to define Un for all n in Z. And we want to obtain the formula, the actual way to write it down. And we just consider the matrix of the following form, which acts on two vectors that looks like that. And then we consider, I like to call it a cocycle. It's not very formal, but actually it does have all the properties of a cocycle. So, so we have this following cocycle A, which is equal to Tn over T everything up to 1, if n is bigger or equal than 1, to 0, to just identity if n is 0, and to Tn plus 1 e minus 1, to T0 e minus 1, if n is less or equal than 1. Then we can write the following equation on the states of the function u. And we have a nice formula on those. Well, we have a nice formula that Rail proved independently and not in regard to this particular case, but it will help us a lot. And it states that if we have some set of SL2R matrices that that satisfy the following two equations, then there exists a one-dimensional subset in which the limit of the logarithm divided by n is minus L for this subset and is L for everything else. That's a nice theorem because it gives us exponential decay at infinity or minus infinity for logarithm of our co-cycles norm. And it gives us exponential decay for one and only one solution. And others will increase exponentially. And the rate will be the same rate, will be L. This L is actually the Lyapunov exponent, which I decided to not define because it's a little bit confusing for people who never encountered it. But we will discuss another way of looking at the spectrum, and it's through generalized eigenvalues. So we will call an eigenvalue generalized if there is a non-trivial solution for which the following holds. So it's basically nicely bounded.
So it's not in L2, yes? You want to say?
Yeah.
Okay.
So every generalized eigenvalue belongs to the spectrum. No surprise here. But it goes further. If the delta here is fixed and it's bigger than 1 divided by 2, but bigger than half, then for almost every number E, there exists a generalized eigenvalue, as in here. So that's a big set, actually. And if we consider the set of all generalized eigenvalues of H, then the spectrum is just a closure of the set of generalized eigenvalues.
What is special about the value half for delta? What is special?
I'm not sure, but I think that it's mostly some computational stuff that actually might even be up for improvement. Because actually that's a problem with a lot of proofs in this area. And that's why I am doing my best to escape giving them. They are at parts exceedingly computational.
Okay.
Right. So far, no one's lost, right? So this theorem gives us a very good idea of why we want to study the solutions of the equation that we discussed. And that's because the spectrum is actually defined by them. The spectrum is a closure of the set of the generalized eigenvalues. That's nice. All right, so we can do better. We can define a so-called subordinate solution, which will be unique because it will be a solution for which this limit holds. This is not a normal LP measure, LP space measure. It's sort of a complicated construction, which was adapted specifically for this part. And so we will call a solution subordinate, just subordinate, if it's subordinate at both minus infinity and infinity. So we have our measure. We can decompose it into 3 parts. And if we consider only 2 parts of it, singularly continuous and pure point, then it is actually supported by the set of all points for which our equation will have a subordinate solution. It's a little bit worse with absolutely continuous stuff because we will have we'll have to consider those numbers E for which the equation has no solution subordinate at either minus or plus infinity. And then the union of those sets will give us an essential support of the absolutely continuous part of our universal measure, but not their actual support, which is a shame. But what can you do? Then one can write actually quite explicit ways to define the absolutely continuous, singularly continuous, and pure point spectra. Here they are. So absolutely continuous is no subordinate solution at either plus or minus infinity, and essential closure. Singularly continuous is inside has the set of those numbers that which the equation has a subordinate solution, but is not square summable. And for pure points, the equation should have a non-trivial square summable subordinate solution. So far, so good? Okay, I'm assuming yes. So the next part is a big one and an important one. So dynamically defined potentials. Before I'm going to explain why I want to define potentials dynamically, I will give a little historical remark. So people studied Schrödinger equations as a part of a bigger set of self-adjoint operators.
Do you understand, right, that in all these papers V is already random? Previously you had V deterministic function, but now you are going to random potential, so not quite.
I'm sorry?
Okay, in the papers, cited papers, Golshay, Bolchanov, Pastor, etc. Pastor, V is always random potential, I guess.
Yeah.
But previously in your presentation, V was always a deterministic function.
Yeah, we are going to get to that. We're going to consider a little bit different. And I will explain why I want to do that in a minute. So people studied Schrödinger equations, and then Molchanov and Pastur defined Schrödinger equations for random potentials for the first time. And then Pastur developed the framework. And then people realized that it's actually a nice way of studying Schrödinger operators. And then Sinai, Chulayevsky, and the big company of other authors.
Have you seen the recent book by Chulayevsky and Sukhov on this topic? Recent book
No, I haven't.
2 years ago, 3 years
Really?
ago. A few years ago, there was a book by Chulayevsky and Sukhov on this topic.
That's great. I'd love to read that. Is it in Russian?
In English, of course. But it's easy to find in the internet.
Yeah. Great. Thank you very much for recommending it. Right. So the topic had a second breath in the 21st century, when Bourgain, who is a Fields laureate, started developing I would assume almost periodic potential case, although there might be works of him that cover more broad area. And then Artur Avila started working on this area, and what he did, he basically took every major conjecture there was in the almost periodic potential theory and proved most of them one after another, which was really impressive because some of them were around since the 80s. And so when he was awarded the Fields Medal, his work on almost periodic potentials for Schrödinger operators was mentioned specifically as a part of his medal, his nomination. And what exactly is a dynamically defined potential? Well, we consider a function V, which is dependent on some omega. Omega belongs to a measurable set. And it's just defined in the following manner. We have an invertible measure preserving transformation T. We have a measurable bounded, usually continuous, but not always, function f. And we consider f from T and W.
I believe it's the same that to say that V is strictly stationary random process. It's equivalent.
Well, it's not actually, because in this particular case, we do have a well-defined algorithm to obtain any next Vn.
Okay, but in distribution, okay.
Yeah, in distribution, yeah.
It's a stationary, general stationary process. Okay. Okay, I can live with this.
Right. So we have a family of Schrödinger operators indexed by the elements of the measurable set. And we want to study this family. The natural question is why? We seem to be doing good with nice, well-defined singular Schrödinger operators, and now for some reason we want families.
Sorry.
A lot of cases that people are actually interested in have potential functions of quite particular properties, like there is an almost material operator, which is where the potential function is a cosine of some expression. And there is a big case of studying the potential function being an exponent of some equation. And all those cases are, in all those cases, this function is periodic or almost periodic in nature. And it's sort of nice to study a family of transformations. This potential function can endure, because then we can apply quadratic theorems to receiving nice results about any particular case of the potential function. And very well-studied examples are crystals, or just cases of periodic potential, where the measurable set is just the ZP, the set of all oh God, I forgot the English name. I'm so sorry. Z factorized by PZ, and then the invertible transformation is just the shift, and the measure assigned to each number is 1 divided by P, B meter. And another case that everyone really loves to study is almost periodic structures. This happens when the set we're working with is the space we're working with is compact abelian group. It has a Hahn measure, which we can normalize and use. And we consider minimal translations, where minimal means that every orbit is dense. And for almost periodic structures, actually a lot of things are known, but there are a lot of things that are yet unproven. And I will pose a few problems when we get to the end of the talk. Special cases of interest are the case of a torus, which gives us quasi-periodic potentials, and the case where the space we're working on is a counter set, which gives us limit periodic potentials. So just to put it all in the perspective, they're both in the almost periodic structure case. But if we, if we take something that is both limit periodic and quasi-periodic, we just get periodic case. All right.
Why do, in case torus, we have quasi-periodic, not just periodic?
Well, it's a name, really. But the reason for that is that it's actually a little bit more complicated. I'm trying to think how to explain that without Right. So I have my now I can.
Please can you repeat again? What do we imply when say quasi-periodic?
Yeah. So let me just write the form of a quasi-periodic potential. So here we will have W and alpha belong to our torus. And if the entries of alpha are not linearly dependent over the rational numbers, then it will not actually be periodic. It will be dense and it will be rotating along, rotating a modka. So if there is no rational dependence, it will not be periodic, but it will be as close to the starting point as you want it infinite number of times. And that's why it's not periodic. Is this better or is it not?
V omega 10 equals some function. This function is periodic, but we have some argument which differs from period. Yes.
Okay. Imagine a two torus. Just a donut, right? So if you start from a point on a two, let's imagine that the function f is not here, that it's just an identity. So the potential is W plus n alpha. So we're starting to make steps on this torus. Actually, you know what? Let's imagine a circle. There's nothing easier than a circle. So we have a point W where we're standing on a circle. W. And let's say that this is alpha. So we make a step, then we make another step, and we make another step. Should have taken a longer alpha. Doesn't matter. So we do not actually come back to W. Because if alpha is rational, then we will go along the circle for infinity without ever coming back. But we will come back arbitrarily close to W infinite number of times. So that's why it's quasi-periodic, but not periodic.
Thanks, now it's clear.
I'm glad that is clear. Right. Let me see if I can move it. Yes, I can. Great. So someone mentioned a case of probability of random potentials. We're not going to pay them a lot of time because I thought that it's quite out of the scope of the seminar. But yeah, people are studying them. They are interested in them. The setting is just that we take an interval and we take its z times. So we study basically sequences of points from the interval. We have our invertible transformation T just being a translation. We have a measure that is a product of measures. And then some different cases of function give us different cases of of how the operator behaves. So there's Anderson model, which everyone really likes, and that's a model of a medium where waves do not diffuse. And physicists actually are very interested in this model, so many people study it. There is a sort of a generalization of an Anderson model. Anderson model is where we only depend on the first element of the sequence W. Then we can depend on the first n elements of the sequence W, which is much harder to analyze, but people managed. It was one of Artur Avila's works again, but I think it happened after he received his Fields Medal because it was fairly recent. And then, of course, we can just consider a general function that is continuous on this weird set of ours. And it's even more hard to analyze, but yes, some results were known. Now, we can still define a measure for, a measure on the set of possible eigenvalues and everything else in a very similar way to the spectral measure. And now all our results will be for ergodic families. Ergodic families is just when the measure that we take on the space omega is ergodic. We would like it to be uniquely ergodic or even strictly ergodic. Strictly ergodic means ergodic and minimal, but it's not always the case. And I will highlight when that happens. So we have an ergodic family of some Schrödinger operators. And then we say that there exists a set such that for almost all omega, the spectrum of the operator is exactly this set. And moreover, the set of omega such that E is an eigenvalue of the operator is of measure 0 for all, not just almost all, but for all possible eigenvalues. This is a very nice, this is by Paster. This is a very nice result because it says that the spectrum of operators in ergodic families are very, very homogeneous. And the proof was some, the sketch of the proof is the following. We can consider T invariable measurable functions, and by ergodicity, they will be almost everywhere constant. And then we can consider functions that associates to some fixed open interval of the real line, the dimension of the range of its associated spectral projection. And this dimension will be 0 if and only if this interval does not intersect the spectrum of the operator at all. So almost everywhere, constancy will imply that either this interval does not intersect the spectrum almost surely, or that it almost surely does. And then we'll vary our interval in some countable way to get the almost sure constancy of the spectrum. And this reasoning was modified soon after to get better results. So first of all, we can consider still the almost continuous, singly continuous and pure point parts of the spectrum. We can apply minimality to turn mu almost epsilon into all of them. And if we have a compact metric space, we have a homomorphism, we have it minimal, and we have a continuous function. It's a very, very usual setting. We will see it 5 or 6 more times. Then we can actually find a single set that will be the almost continuous spectrum for all Schrödinger operators in the family. Right, so a little different way of looking at those things is if we study uniform hyperbolicity, which dynamists really like to do. So we have this whole cycle AE. Do I need to remind what is it? Because I think it was quite a while ago. People might have forgotten.
Yeah, it's better to remind.
Right, so let me go a little bit upwards. So we have the equation, and we want to define un plus 1 un through just u1, u0. Then we define a co-cycle in the following manner, which is just the product of matrices. And those matrices are defined like that. So basically, we take this part of the equation here. Then we turn everything into an equation on 2 vectors. And if we study this co-cycle, where were we? No, too much. If we study this co-cycle, we can say that it's uniformly hyperbolic for a fixed E. If for every constant C we take and every constant lambda that is bigger than 1 we take, the following is true. It means that it grows really, really rapidly. So we have the uniformly hyperbolic subset of complex numbers, and it's just a set of those numbers for which the co-cycle is uniformly hyperbolic. And we can find
in your basic example with Schrödinger equation, it's uniformly hyperbolic, yes?
Yeah.
What conditions on V is necessary to impose to have this property, uniform hyperbolicity?
Oh,
you had your basic example when you have the product of matrices. The question is, does it uniformly hyperbolic for any V or some condition is necessary for the potential?
Oh, no, I'm afraid the condition on the potential is definitely necessary.
Okay,
And
what type?
Be an easy one. It will not be like, oh, well, all almost periodic potentials are uniformly hyperbolic. Okay. Actually, uniform hyperbolicity depends on E. So for different E, we will have different results on uniform hyperbolicity of the co-cycle. So it's unfortunately not as easy as that. That would be nice, but no such luck for us. So we have the uniformly hyperbolic set. We can define the Laplace exponent. Do not dwell on what that means, L, for this set. And then we can define a non-uniformly hyperbolic set, which says that, which is a set of those numbers that do not give us very good hyperbolicity, like uniform hyperbolicity, but still give us some hyperbolicity, because if this limit is not 0, it means that the logarithm of norm grows really rapidly, which means that this thing has exponential growth. And of course, we can define, oh, that's a mistake. We can define a set that is a set of what is left, and that's the set where the logarithm grows not fast enough, and so this LE is just 0. And we can rewrite the statements we're having about the continuous spectrum, well, not just continuous spectrum, all parts of spectrum really, in a hyperbolic and non-uniformly hyperbolic way, which is sometimes more convenient because uniform hyperbolicity is a property that can be explicitly counted by hand. So sometimes, for some cases, the equations are not nice, but sometimes they really are. I think that they are nice for the so-called almost Mathieu case, which is excessively studied for some reason by everyone who ever did anything in this particular area of mathematics. And if you can write those equations and have them nice, then you can have an explicit formulation of how your spectrum looks. So we have, first we have that this subset where LE is equal to 0 belongs to this subset big sigma, which we defined earlier, which is the subset of basically all, which is basically the spectrum. And the spectrum belongs to the non-uniformly hyperbolic case and Z2. So there are some conditions to enforce, like we like compactness, we like homomorphisms, we like continuous functions, we like minimality. That will give us the exact equation. Would be nice to have that Z is just pure point spectrum, but unfortunately, no, not true. There are some other theorems on the same in the same field, I guess. So if we have a Gaussian-Borel probability measure, then we can also say that the Lebesgue measure of Z is 0, and that we have no absolutely continuous spectrum to speak about. If we have non-atomic Gaussian-Borel probability measure, and the set of functions of this set of functions of this of the kind that for them absolutely continuous spectrum is empty is a residual set. So at this point, you mostly can't do anything else, and you have to specify more conditions to obtain more results. So we are going to discuss almost periodic potential.
Can I ask about measures?
Yeah.
Can you tell us something about ergodic Borel measure and non-atomic?
Oh, the definitions.
Yeah, just remind.
Borel measure is basically a measure in Borel sigma algebra. A probability measure means that the whole set has measure 1. A Gaussian measure is, okay, that probably should be written. A Gaussian measure is such that any E should T minus 1.
Any when a set has a 0 or 1 measure.
Yeah. And non-atomic means that we do not have atoms.
What does it mean? We don't have atoms.
So an atom is a set that do I have to write it? I think I have to write it. Right. So, by the way, a very important thing, I sort of didn't state that explicitly. I am assuming that the measure is invariant regarding t. So it's very important to keep in mind that. Right, no.
May I ask a bit philosophical question?
Yeah.
After all, what we need the eigenfunction for? We want to expand some any function as superposition of these functions, right? So clearly they're not the eigenfunctions for continuous spectrum. They are not in L2. So what class of function we can expand after all, after we do all this analysis? What is the class of functions we can represent as linear combinations of eigenfunctions? It's bigger than L2, but how big it is?
That's actually a good question. Let me think about it for a second.
Okay, we can carry on. It's not necessary to, but it's just also philosophy.
Yeah. No, it's a good question. It's interesting that it was not explicitly stated in any papers.
Yeah, it's not usually stated in the papers of this topic. That's strange, because we want to expand some reasonably wide class of functions, linear combination of eigenfunctions. So that's after all the whole game is about. But what is the class function we can expand after all? It's not stated usually.
Yeah, that's actually, you're right. That's really weird. That's a major problem with this topic. Some things are assumed to be known by the reader, but they date back to papers that are impossible to find. If you want to, I can try to figure it out or actually ask the person who introduced me to this topic and come back to you.
Okay, thanks.
You can write your email in the chat if you want me to do that. Actually, that probably would be the best to conduct. And I had a question about non-atomic measures, right?
Right.
So an atom is. Can I delete something? Yeah. So we have a set A of non-zero measure. And it's called an atom if for any set B such that the measure of B is 0. And that's, I mean, an atom is because it can't be divided further. Like if we divide it further, the measure is suddenly 0. This happens, for example, if we have some bad measure, like I take an interval and I put my whole weight of the whole measure in one point. So every set will have measure either like, let me draw it. Like I have an interval and all my weight of my measure is here in this point. So any set I take will be of measure 0 or measure 1, with no in between. And that means that every set I take is an atom. Well, every set I take, if it contains this point, is an atom. This is an atom because I either take another set that contains one, and then the measure of the set is not less than the measure of the initial set. Or I take the set that does not contain one, then its measure is 0. So it's an atom.
It is an atom. Mm-hmm.
Yeah, it's bad. People don't like to have it. Is it okay?
And non-atomic means that we don't have.
Yeah, non-atomic means that we don't have any atoms.
And what about measure it's also not 0 or 0
What?
almost everywhere.
I don't quite hear you. Can you please repeat?
So what do we have with non-zero measure sets? Which non-zero measure sets we have in non-atomic case?
Well, the back measure is non-atomic. Good measures are actually non-atomic. A counting measure is non-atomic. Atomic measures are quite big outliers. It's not something that happens often.
Thanks.
It's kind of hard to invent an atomic measure that assigns that doesn't look really trivial, like the one I used as an example. Like if you try to invent an atomic measure, you will probably run into some difficulties with that.
All discrete distributions in elementary probability theory are atomic, by the way. Okay, that's a side remark.
Oh, okay. But wait, you say elementary distributions?
I mean, all discrete distributions in the fresher course of probability theory are actually atomic. Okay.
But if you have, wait a second. But if you have distribution,
the discrete distributions means automatically that the measure is atomic, but we won't really have something like density function here. Okay.
yeah.
It's not it's just a side remark, not important.
Okay. Right. So let us move on to almost periodic potentials. We call a function, a bounded function, almost periodic if the set of its translates has compact closure in our set of functions. So we translate the function from n to n+1, and we consider the set of its whole translates, and we consider the closure. It's a good thing to study because if we have some cosine or we have some exponent or we have something like that, then we can study all its states at the same time by considering the Gaussian family. So good. And every almost periodic potential obviously can be realized as an element of an Gaussian family because we can equip this closure with a group structure just through taking limits, and we have a shift that is very nice and very simple. And the measure will be the Ha measure on this closure equipped with an abelian group structure. So if the function is periodic, then we immediately know how the spectrum looks because we take the trace of our call cycle and we oops, that should not be Z, that should be. Yeah, I'm sorry, that's a problem of comprising a few papers into one. So we have an immediate and very good way to define the spectrum. And well, cases that are not periodic are not as good. For example, if we consider a so-called almost mature operator, I'm sorry, it just has the potential of a very, very simple, very nice form, and you'd never think that there are any problems with that, like just a cosine. But here's the thing: we can have the irrational relationship between W and alpha, the one that I've mentioned before. And suddenly this case of almost mature operator is not simple anymore. There was a so-called 10 Martini problem, which was posed and rumored to bring 10 Martinis to the guy who solved it. And it was solved after a few years, quite a few years, by Avila and Zhytomyrskaya. And I think that they were not given their Martinis.
Zhytomyrskaya.
Zhytomyrskaya, yeah. But it's a very simple. It just asks you to prove that the spectrum is a counter set, which doesn't sound as a formulation all that hard, but required them a very long paper, exceedingly technical. I tried to read it, it was horrible, just to prove this simple fact. And actually, that's where we have all the Avila results that brought him his Fields Medal, among other things. So many of them are on counter properties of the spectrum. For example, if we have a compact set with a minimal ergodic homomorphism, and we have some abelian, I note that I am going to give you a setting that is even more general than almost periodic functions, potentials. But you can think of it as almost periodic potential setting, if you want to. So we have an infinite compact abelian group, and an element of this group, and a known to continuous map for which the following holds. So that actually includes almost periodic potentials too. And so then the uniform hyperbolic, the sets of such functions, not numbers. We usually consider the set of numbers for which it's uniformly hyperbolic, but now we're considering the set of functions with a number e fixed. So the set is open and dense. And moreover, if we consider the set C as for which of such functions which the spectra is counter, the set will be residual. So it means that actually counter spectrum is very generic and happens to us a lot, which was very unexpected. Like nobody thought that this would happen when they proved it. Right, so even easier, even more specific cases, so-called limit periodic, case where the potential is in L infinity closure of periodic points. And a lot of stuff in this scenario was proved for counter groups. So suddenly we have a lot of counterality. And Artur Avila proved that if we're working with a counter group, then there is a dense subset, which is also a countable intersection of open sets, such that and the subset of all continuous functions from our set to real numbers, such that for any function in this set, the spectrum of our Schrödinger operator for any W will be a counter measure zero set, the back measure zero set. And then Dynamically and Gunn exploited the same setting to show that there is a dense set such that for any function in this set, the spectrum is a counter set of positive feedback measure, and HW has a purely absolutely continuous spectrum. People were quite surprised at those results because they expected limit periodic potentials to behave at least somewhat similarly to periodic potentials. And purely absolutely continuous spectrum, well, okay, let me probably get to another theorem and explain why everything was so surprising. So, in the setting of theorem A, the Schrödinger operators were proved to have purely singular continuous spectrum. But then a small assumption led us to having pure point spectrum and exponential decay of all eigenvectors. And the assumption was not even a big one. It just stated that maximal frequency integer sets had some property on how fast it grew. And that was not what people expected to happen, because first, early works were aiming for absolutely continuous spectrum. Then pure point spectrum is as far away as from absolutely continuous as possible. And also the strength of localization result is actually quite good. Like it's almost uniform localization. So it's surprising to get results for such a big and not really restricted set of not really that restricted set of possible potentials. Right, and I want to finish by stating some open problems, just in case people become interested in them. So we know a lot about dense subsets of absolutely continuous spectrum, and we know the spectrum is a counter set. But is it possible that that there is a suitable dense subset of all continuous functions for which the Schrödinger operators will have a pure point spectrum for almost every omega?
That's Pastor Molchanov example, if you know it, for random potential.
Was it done?
Of course, many years ago.
Really? Because I think that I have encountered this as an open problem in a paper that was published.
So pure point spectrum, no, that's very, very old problem solved 20 years ago.
5 years ago? That's interesting.
Many years ago, 20.
I wonder why it was never, what is never known to the...
Under some problem, okay, it's a pure point spectrum.
No, the Anderson problem, but I'm currently talking about limit periodic potentials, different setting.
Oh, okay, fine, okay, that makes sense, yeah. You're talking about nearly periodic potentials.
Yeah, this is for linear periodic potentials.
No, linear, of course, linear, but
limit. I'm sorry.
Both problems are linear, but
no.
You're talking about almost periodic potentials. Okay. So
we have limit periodic potentials that are basically limits of periodic potentials, and for them there are some problems that can be easily stated but are not yet proven. So this is the first one. And we also want to know if the spectral type of our Schrödinger operator is the same for all omega, which we kind of hope for, but it's not the case for more general families and for quasi-periodic potentials, actually. But it's not quite clear if the same problem will arise with the limit periodic case, because we have quite a strong approximation in this scenario by periodic potentials. And of course, it's interesting if the spectrum is always pure. We know that it's not the case in general for almost periodic potentials, but maybe with limit periodics. So I suppose that at this point, I should stop and ask you if you have any questions. Right. Shall I assume that this is a no? Can someone please confirm that they're hearing me?
Yeah, we do hear you, but so apparently there are no questions.
Yeah, but I sort of killed it with too much notation, right?
No, I guess it's okay.
Right, so I should probably give some links to papers. So there is a very nice, will I be able to write? There is a very nice survey and actually a course by David Dynamically, given at Centre International Bernoulli in 2018, I should think. I will send a link to the course in the chat for those who want to watch it. It's very, very user-friendly. He's a specialist of the field. He wrote a ton of papers in those, and he will probably be able to give you even better explanations of stuff you didn't understand that I did. There is a paper by Kartajan. I have to Google how to write his surname correctly. Give me a moment. Oh, that's hard. Right, so it's Adieya. Can I just write it in Russian? The name of the paper is right. Maybe I should just send you a link to this. Oh, whoops. Right. I'll just send the links to the chat to all the stuff that I wanted to show you. Sorry, I should have prepared my links better. So first we have
Я там скинул правильное написание в чатик. На всякий случай.
Спасибо. Да, это здорово. Right, so the paper by Fadiev and Tehtajan is, yeah, I'm very bad with names. Is just, let me just send you the link to it. And that's the first one. And the CIB and the CIB lectures can be seen if you go to this link and go to the schedule and then press on the dynamics lecture. And that's I think is the most friendly way of getting acquainted with the topic is listening to the Mannix lectures. They are approximately 4 hours worth time. They are very nice, not hard to follow. Right, so I think that's it. I thank you all for your attention. It was very nice to actually have people ask me questions during the talk. It doesn't happen often.
Okay, let's thank the speaker. So I guess that's all. Thank you very much.
Thank you.